continue on here, and now we're going to talk about numeric summaries, all right? All right, and so numeric summaries, these are values, okay, that we can use to summarize a sample of data, okay? So we, the idea is, we have a sample of numeric data, or sample of data, and in particular, a numeric variable, okay? So you have to imagine something like you've got, 100 data points, right? Earlier we looked at, all those goals that those soccer players scored or whatever, and we can imagine another data set where we have, 500 different people, and maybe we ask them a question, okay? We ask them something like, what was your SAT score or something, okay? So we have numeric values for a bunch of people, and rather than having to look at every single individual value, okay, maybe we want to create ways to summarize that, okay? So we can summarize our data, and we're going to call these, with a few values, and we're going to call these sample statistics. Okay, so sample statistics are just values that we can use to describe or summarize a sample of data, okay? And so in particular, we're going to look at sample statistics that summarize numeric data, okay? Okay, and we'll learn a few, but this is a concept that you guys are already familiar with, okay? So, for example, as students, you guys are familiar with the concept of a GPA, right? Okay, and so the GPA, your GPA is just a single number that is supposed to summarize your entire academic career, right? Okay, this is just a single number to summarize your entire academic career. Okay, and so, and I think because you guys are familiar with this idea of a GPA, you're familiar with its usefulness, but you're also familiar with its limitations, right? So, if you had to pick people to be in a study group, okay, and you were able to know that person's GPA, it would be useful, right? You'd be like, oh, I want to study with the people with high GPAs or things like that, okay? And then if you see someone with like a, 1.5 GPA, you're going to be like, I don't know if I want you in my study group, and things like that, right? It's good to kind of just summarize rather than saying like, oh, what grade did you get in your chemistry class, and what grade did you get in your English 1 class, and what grade did you get in your writing composition class, and trying to get every single one of these details, okay, or getting the entire transcript, you just got this single number, which is pretty useful at summarizing overall how good of a student someone is, right? And the GPA, it tries to balance things out by weighing the quote hard classes as more units and the things like that. But we also know it doesn't capture the whole story, right? Maybe you're a great student, but then you had like one bad quarter where something terrible happened in your life and you did really poorly, and you'll say like, oh, that quarter tanked my GPA or something like that, or that semester did really hurt my GPA. And so you understand that there are limitations to trying to boil something complicated into a single number, okay? But it is also useful to boil things down to a single number, right? So, yes, question?
Can you explain the difference between weighted and non-weighted?
That doesn't
apply.
Yeah, I mean, yeah. So as far as GPAs go, yeah, they have weighted and unweighted GPAs, but they don't really matter. I mean, okay, it's just different different formulas for calculating this, how we're going to get this single value to summarize your life, right? So, so that's what sample statistics are. Okay, we're taking a bunch of data and we're boiling it down to a single number because it's easier for our brains to deal with single numbers, and we can compare groups if we boil them down to single numbers rather than having to look at all of the details, okay? However, when you boil things down to single numbers, you lose a lot of nuance, and so that's the other side, okay? So there's kind of this balanced thing where, you know, you look at graphic displays with histograms, you also boil things down to single numbers, but again, anytime you're just trying to summarize something complicated, something's bound to be left out, okay? Okay, so what do we have? Okay, I wrote, GPA is a single number that summarizes your entire academic career, okay? This is very useful when trying to make quick comparisons. Quick comparisons between students, okay? At the same time, we lose detail. That's loose. Okay, so and we have a bunch of other sample statistics, other ways to summarize things. So, you know, if you're into sports, okay, like or if you know, especially if you do like fantasy sports or something, you're trying to summarize. A lot of times you'll have these sports statistics, right? So if you watch baseball, you know, every time a player comes up, they'll say things like, you know, this baseball player's batting average is this, or their on-base percentage is this. And it's just like a single number that's supposed to capture how good of a baseball player this person is, okay? And it's complicated, okay? But a lot of times, but it's also useful when trying to make quick comparisons between people, okay? Or, you know, same with football, they have like passer ratings for the quarterback. You know, for basketball, you have like shooting percentages and points per game and things like that. Just these single values that are trying to boil down how good of a player someone is, okay? All right, so we have, we've got this. And so as far as today's lesson goes, we will learn numeric summaries that tell us about the center, center of a sample of data, okay? And those are things like the mean and the median, okay? And we also have numeric summaries that describe the spread or the dispersion. Okay, and these are the standard deviation, and in that same breath, the variance, okay? And also we have the IQR, interquartile range. Okay. Our textbook kind of makes a point of distinguishing between numeric summaries that are useful for skewed data versus symmetric data, okay? And the truth is these numeric summaries, or these sample statistics, all four of them can be calculated for any sample of numeric data, okay? So all four have the above sample statistics. So I'm kind of using sample statistics and numeric summaries interchangeably. Can be found for any set of numeric data. Okay. But some, and including our book, some may say if the data is symmetric, use mean and standard deviation, which I'm abbreviating here. And if the data is skewed, use median and IQR. Okay. But again, you can calculate the median and IQR if the data is symmetric. You can calculate the mean and the standard deviation even if the data is skewed. But some may say that in certain contexts or in certain situations, we may prefer one set of numeric summaries or one set of sample statistics over another. Yes, question?
What's an IQR mean?
The IQR is the interquartile range right here.
Which means?
I will explain. Yeah, so yeah, just because I wrote interquartile range, I don't expect you to know what that means, or even standard deviation or what variance means. Okay, I will explain all of this. Right now, you just know they are numeric summaries that describe spread or dispersion. Okay, and that really is the big picture idea that you need to know. Okay, so far so good? Can I flip? Okay, so let's talk about the mean. I think we are familiar with the concept of the mean.
It's an average.
Yeah, it's the average, okay? We add up the values, okay? The symbol that we use for mean is X bar. Okay, this is the simple, this means sample mean. And what do? We add up the values and divide by how many we have, right? Okay, and I think we are familiar with this concept. If we want to write a formula, we would say X bar is equal, and I write this symbol. This means sum. It's like a sideways M. Okay, sum the x's, divide by n, right? So sum x means add up the x's, add up the x values, and then n is the sample size, so that's how many values you have. All right, so sum of x over n, that's just another way of saying add up the values and divide by how many you have. Okay, that's X bar, the sample mean. Okay, our conceptual definition of the mean, this is probably more important. is that this can be thought of as the balance point of our data. All right, what do we mean by that? Okay, let me copy this little dot plot here. So here we took a survey of people and we said, what was your ACT score? So the ACT is it's a standardized test. It's kind of like the SAT exam. It's like you take it, colleges look at it, and they say, oh, you scored this on the ACT, you know, you can come to our school. Oh, you scored this on the ACT, you can't come to our school, okay? So that's what it is, and so here's the dot plot. You can imagine each of these dots being like a rock, okay, or a stone, and you know, we're putting it on a plank, okay, on a seesaw, and we say, okay, where would I want to put the little triangle so that the seesaw stays balanced? We would put the fulcrum right here, right, you know, like 24.5, okay, and this is where the seesaw would be balanced, okay? So if we put x bar is equal to 24.5, okay, the seesaw is balanced. Okay, so that's our balance point of our data. And we would get that if we added up all of these things and divided by how many we have. You know, if I put the seesaw, the little fulcrum at 29, the thing would tip over, okay, one way. And same thing, if I moved it the other way, it would tip over the other way. And so we can think of the mean as the balance point of our data. Is that okay? When our data is skewed, the balance point gets pulled in the direction of the skew. Okay, so you know, when you're on the seesaw, you know that if you lean back, you get a little bit more leverage, right? Because now your weight is shifted away from the fulcrum, and so now you're more likely to go down and things like that. So if the data is skewed, the balance point will shift in the direction of the tail, or shift in the direction of the skew. Okay, and so that's why the textbook says if you have skewed data, we might prefer not to use the mean, okay? Because the mean is affected by extreme values, like in a skew, okay? Is that okay? So in the textbook, there's kind of this graph here. So here is here's a histogram of this is baseball players' starting salaries, okay? Or not even starting salaries, just baseball players' salaries, right? And we would say this distribution is skewed in which direction? Skewed to the right, okay? And so in order for it to be balanced, the mean gets put right here. Okay, the mean gets put right here, and this is where the distribution will be balanced. Okay, but it's if we look at it, okay, this makes the average to be at around $3 million, $3.2 million. Okay, but if we ask what percentage of players make less than $3.2 million, it's about 70%. Okay, so is it fair to use $3.2 million as the average salary if 70% of baseball players make less than that? No. Maybe, maybe not. I don't know. Okay, but you know, you have people making $33 million a year, or you know, $20 million a year, and that's going to pull out the skew. Okay, you know, the minimum that you get paid if you're a pro baseball player is $400,000, okay? And you have, over, over almost half of your players making less than $1 million a year, okay? And so, is it right to say the average is 3.2? I mean, that is the mean, but maybe it's not the best number to represent the data, okay? Question?
Yeah, this chart is unimodal, right?
Yeah, we got one mode here, okay, and it's skewed right, okay. All right. On the other hand, we have the median, okay. Okay. The median can be thought of as the halfway point. Okay. Half of the data set is equal to or above the median. And half of the data is equal to or below the median. Okay, so the median is the halfway point. If we were to draw a histogram, you can think of it. So let me kind of just. So here I've got this thing, and we can think of as the median as, if I wanted to split this into two pieces that are of equal area, where would I draw my line, okay? And yeah, it's a little complicated, but I don't know. Maybe somewhere around here, I don't know. And we would paint one side, and we can say, maybe these two sides have equal area, maybe not, I don't know. I'm trying to, that's the idea here, okay? So the idea being if this is the median, both of these sides have equal area, okay? So this is the median, we have both sides have equal area. And so the median is not affected by extreme values or skew. Yes.
It's not numeric middle, it's like the spatial middle.
It's where you're going to have half of the values are equal to or above the median, and half of the values are equal to or less than the median. If we were to create a histogram, we can visualize the median as the spot where you're going to have half the area above and half the area below. Okay? But as far as the median, as we define it, it's a value. It's a numeric value, but you're going to have half of your values equal to or above, half of your values equal to or below. Okay? Yes?
How does the median compare with typical?
So typical, I've been using the word typical as kind of a way to avoid using the words mean or median. A lot of times when you hear the word average, average is thought of this kind of represents the concept of mean generally, okay? But yeah, the mean you get by adding up the numbers and dividing by how many numbers you have. The mean is affected by extreme values. The median is not, okay? So if you have symmetric data, so I'll write this. For symmetric data, okay, the mean and the median will be similar in value. Okay, that's for symmetric data. Here's a question for you. All right, you guys, can I flip to the next slide and put up a question here? All right, well, I'm going to. Okay, so imagine data is left skewed. Okay, so let's say we have left skewed data. Okay, how does the mean and the median compare? How do the mean and median compare? All right, pull out your cards. Let's see. Okay, so pick green if you think mean is less than median. Pink if you think mean is greater than median. And we'll say orange if you think mean is comparable to median. And yellow if this is not enough info. Okay, go ahead and think about this. We have data that is left skewed, so we've got something that looks like that. Let's think of what do you think this will be?
Like green and pink is the same thing.
Huh?
Green and pink is the same thing.
No. Green and pink are the opposite things, right? Mean is less than the median versus mean is greater than the median. Okay? All right, so think about this. Okay, you guys have your cards. Turn to your neighbors. Try to discuss what you think the answer should be. All right. Have we come to a decision about what we think our answer is? Okay, go ahead and hold up your answers. Let's see what you guys think. Okay. So we're split between green and pink. Some people think not enough info. Okay, the answer is green. Okay, The mean will be less than the median. Okay, this is the correct answer. All right, let's talk about this. Okay, let's just try this with a simple example. Okay, we'll look at let's just say family. We've got family A and family B. Okay. All right, and so the kids in family A, I'm gonna just say there's 5 kids. Okay. And let's say their kids are 18, 17, 16, 15, and 1. Okay? All right. And I wrote them down this way because generally when you give kids ages of kids, you start at the highest and you work down, but then when you write them, you generally write your smallest numbers in the beginning, right? Okay. And then we'll say family B, let's just say 18, 17, 16, 15, and 14, okay? So you can imagine, maybe family A and family B were friends and they were having kids together or whatever, okay? Whatever, sometimes people plan these things and sometimes they don't. And so anyway, family B and family A, they both ended up with 5 kids. And pretty much, if we look at the oldest 4, they're the same age, right? But the big difference is the youngest child, right? Over in family B, the youngest child is 14, and in family A, the youngest child is 1. And, you can think of a backstory for both of these families. But let's...
Those five numbers added to 67.
Okay, so I'm just gonna make a little. Actually, this is not gonna. This is gonna be 2.
67 divided by 5.
All right, hang on a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14. Okay. So here we're going to create a dot plot for family A and a dot plot for family B, okay? Okay, so dot plot for family A, I'm going to put a dot here at 1, a dot at 15, 16, 17, and 18, okay? And we can see this would be very loosely, but we would say this would be left skewed, right? Okay, because we got one extreme on the low end but not on the high end. Okay, and over here we've got 14, 15, 16, 17, and 18. So this is family A, family B. Okay, if we want to calculate the median, where is the median for family A? The median is at 16, right? So this is the median, and we have 2 that are bigger, 2 that are smaller, and 1 equal to the median. Okay, so I can just kind of split this. 16, this is the median. Family B, what's the median? Also 16. Okay, so this is the median. So both families have the same median age, okay? So median is equal to 16 over here, and median over here also equal to 16. Okay, both families have the same median. But if we look at the mean, okay, we would have to add up all of these numbers and all of that. So here I can do. Okay, so family A, we got 67. We divide that by 5. And we get the average to be 13.4, okay? So the mean is 10, 11, 12, 13.4. This is where we would put the mean value. The mean is at 13.4, and this is where the seesaw would be balanced, okay? Because we got one value way down here, okay? Where would the seesaw be balanced over here? This seesaw would be balanced at 16, okay? So over here, the mean is equal to 16, okay? And so we can see that because of the extreme value on the low end, or because of the left skew, and this is kind of the idea of having extreme values on the left end, or a low end, the extreme value on the low end left skew shifts the mean into to be lower. Okay. So if you have data that is skewed left, your mean will be lower than the median. Okay? Whereas if it's symmetric, the mean and the median will be about equal, and if it's skewed right, the mean will be greater than the median. Is that all right? Okay, yes?
And that's just a general rule of
Yeah, yeah.
and this is the exact opposite for right skewed.
Yeah, right skewed, the mean will be greater than the median, okay? And that's like one of the indicators, right? So. Okay, all right, so let me just give you some brief directions on finding the median. Okay, and we can talk about okay, so first step, the most important step, is arrange your values from least to greatest. Okay, and then count how many values you have. And then, so that's going to be your n. Okay, n is how many values you have. And then find the spot where n over 2 are smaller and n over 2 are greater. Okay, and if you have an even number, okay, then the median will be between your two middle values. So the median will actually be the average of the middle two values. Okay, so let's say you have the values 2, 4, 7, 8, 12, and 15, okay? So you count and you say, oh, I've got 6 values, n is equal to 6. So n over 2 is 3, okay? And you would go, okay, I want to find the spot where 3 values are smaller and 3 values are greater, okay? And that's going to be between 7 and 8, okay? So your median
7.5.
is the average of those two values. So you do 7 plus 8 divided by 2, and you get 7.5. That's going to be your median value. Okay. If you have an odd n, okay, you'll still have, you'll go n over 2 values smaller and n over 2 values greater. And then 1 equal to the median itself. So let's say we have 3, 6, 9, 10, 12, 14, 18, okay? So here I've got n equal to 7, n over 2. This is going to be 3.5. We're going to just round down to 3, okay? And then, so we're gonna split this and we go 3 smaller, 3 greater, and this one is, so 3 smaller, 3 that are greater, and 10 is equal to the median. Is that okay? Yes, no? All right, so whatever number you have, or you arrange them from least to greatest, okay? And then you say, how many numbers do I have, okay? If you've got 10 numbers, you do 10 divided by 2, and you say, okay, I'm going to have 5 numbers that are smaller than the median, 5 numbers that are greater than the median, okay? So you just count and you find the spot that splits it into 5 and 5, okay? Let's say you have 21 numbers, okay? Okay, you do 21 divided by 2. That's going to give you 10 and a half. Round that number down. Okay. With 21 numbers, you're going to find 10 that are smaller, 10 that are greater, and that number right in the middle. So you have 21 values. That number right in the middle, that's going to be your median. Okay, and so these are the mean and the median. These are just numeric summaries that tell us kind of where the center, the idea of center is, okay? And what are our 2 concepts of center, the conceptual ideas of center? For the mean, the idea for center is the balance point, okay? On the seesaw where it would be balanced. And for the median, the concept of center is the halfway point, okay? Halfway point. All right, here now I have to talk about measures of dispersion, okay? And I got half an hour. Gonna have to work quickly. All right. So dispersion is a way to measure, are your numbers similar to each other or are they quite different from each other, okay? Are the values in your sample are they similar to each other, or are they quite different? Are the values in your sample, are they similar to each other, or are they very different from each other? This is the idea of dispersion. Okay, so let me just kind of give you an example. All right. Think of the U.S. population. Okay, this would be U.S. population. And we're going to look at the age. Age in the U.S. population. This will be our variable. Okay? Is there a lot of variation in the age of the U.S. population? Yes. Okay. We'll just start off with we'll say lots of different ages. Okay. All right. Think of our classroom. This classroom. All right. Okay. We're also still thinking of age. All right. Is there lots of variation in age in this classroom? Okay. Not as much. Not as much as the general U.S. population, okay? Most of you are probably 20-something, you know, maybe a little older, a little bit less, okay? We might have a few students who are considerably older than everyone else, or a few students who might, you know, still be in high school or something. But by and large, most of you are probably, I don't know, 22 plus or minus 5 years or something like that, okay? And compared to the general U.S. population, the amount of spread or the amount of variation or dispersion is a lot smaller, okay? So I'm just going to just write most are probably you know, between 18 to, we'll say, 29 or something like that. Okay, so this is much less variation than US population. Okay, where in the US population you can be basically from ages 0 to 100-ish, right? Okay, you know, most are probably whatever, 18 to 60 or whatever. Okay, you probably have a huge, large swath of people there. This classroom, something like that, okay? And then think of a second grade classroom.
7 years old.
All right, and think of the ages there, right? So there you're gonna have very little variation, okay? Almost everyone in that class, yeah, something around 7 years old. You might have a 6-year-old, you might have an 8-year-old, okay? But by and large, almost everyone, almost all will be 7, right? Will be 7. So, you know, oops, almost. So as far as dispersion goes, this will have the least variation, okay? And this will have the most variation, okay? And so that's, we can just think of different groups of people. And if we're thinking about age, that's one way, okay? And you can think of other things, like the weight of an animal, right? Okay, weights. And you think of dogs, there's a lot of variation in the weight of a dog. You can get a tiny dog, right? Like a 4-pound, I don't know, like how big's a Chihuahua? It's like 3 or 4 pounds or something. It's tiny, okay? And then you can get like, I don't know, some Russian bear dog, and it's gonna be like 180, 200 pounds or something ridiculous, right? You know, German Shepherd, whatever, that's like a 100-pound dog or something, okay? Whereas if you think of cats, household cats, I mean, yeah, you're gonna have some cats that are fat, but overall, I mean, you're not gonna have a 100-pound cat, okay? That's like severely disturbing if there's a house cat that's 100 pounds, right? Most of your cats are gonna be maybe, I don't know, 7 to 12 pounds. Maybe you got some fatty that's 15 or something, but something like that, right? Huh? Yeah, that's a fictional cartoon, right? So you've got, you know, so as far as dispersion goes, we can think of things that have more dispersion and less dispersion, okay? And so rather than just saying, oh, this group has a lot, this group has a little, we have numeric summaries that actually put a value to this. We can say the standard deviation is 4.2 for this group. The standard deviation over here is 45, okay? And that will say this group has lots of standard deviation. This group has much less, okay? Or we can say something like the IQR over here is 52. The IQR over here is 7, okay? And that will give us an exact amount that says this group has much less variation than this group, okay? Rather than just using these loose terms of saying lots of variation and low variation, stuff like that, okay? And so that's what all of, so if someone asks you, what is the standard deviation? You can give them a formula, but that's not really the concept. The idea behind a standard deviation is it's a way to measure this concept of variation or dispersion. Are the values similar to each other? Are they very different from each other? Does that make sense? Okay, so we'll start off with standard deviation. Okay, standard deviation and variation. Okay, and so again, it's just a numeric summary or sample statistic that, you know, gives us a value, gives us a number describing dispersion. Okay. And so the symbol for standard deviation is S. Okay, and then for variation, or the sometimes it's called the variance, is S squared. Okay, and the standard deviation we can just think of as the square root of the variation, or the square root of the variance. Okay, variation slash variance, they're like the same thing. Okay, so we can just think of the standard deviation is equal to the square root of the variation. Variation, I'll also write variance. Okay. All right, and then we can define the variance, can be thought of as, I'm going to put this as quotes, the average squared distance from the mean. Average squared distance from the mean. Okay, so let's try this out here. Okay, so I'm going to just I'm going to copy these. Oops, I don't want to do that. I'm going to just copy these definitions onto our next slide. You don't have to write them up again, but just so they're here. Okay, the standard deviation is the square root of the variance, and the variance is the average squared distance from the mean. Okay, so let's say we, again, we have two families with 5 kids. Okay, so we'll say family C, and we'll have family D. Okay, so family C, their kids' ages will be 7, 8, 9, 10, and 11. And then family D, their ages will be 1, 5, 9, 13, and 17. Okay, both families, 5 kids, both families, the mean age, if we look at it, the mean age is 9. Okay, so both families have a mean age of 9, and both have 5 kids. Okay, but if we look at the families and we just picture life in family C and life in family D, life looks different for these families, right? Okay? And if we said, if I just asked you which family has more spread or more dispersion in ages, you would tell me
D.
family D, right? It's very clear. Okay, family D, you've got a 17-year-old, this kid's about to go to college, and you got the 1-year-old still in diapers. Okay, family C, they're all kind of, you know, they're all still in elementary school, and then the teachers are probably like, oh, you're another one of family C's kids, or something like that, right? It's very fresh in the memory, you know. Family D, you might have some teachers that are like, oh, you're another one of family D's kids, but it's like, I remember having your brother way long ago, right? So it's a little bit different, okay? And so just very clearly in this simple example, we can see family D has a lot more dispersion, okay? Well, let's figure out the numbers here, okay? So we figured out the mean, right? How did I do the mean? We just add them up and we divide by 5, okay? And so here we want the average squared distance from the mean. So what I'm going to do is I'm going to find the distance from the mean, okay? Distance from the mean, okay? How do we find the distance from a value?
1 to 9, 9 to 17.
Wait, okay, so what I'm going to do is I'm going to just subtract 9 from each of these things. I'm going to take the difference, okay, and we say, you know, how far is 1 away from 9? Okay, it's 8 below. How far is 5 away from 9? It's 4 below. How far is 9 away from 9? 0. How far is 13 away from 9? It's 4. And how far is 17 away from 9? It is 8 away, okay? So these are the distances from the mean. Is that okay? And then I'm going to square the distances. the squared distance. Okay, and so all I do is I just take each of these distances and I square them, right? So -8, anytime you square a number, you're always going to get a positive, right? Negative times a negative gives you a positive. So -8 becomes positive 64. 4 squared becomes 16. 0 squared becomes 0. 4 squared becomes 16. And 8 squared becomes, 64. Is that okay? Squared distance, right? And then here we would want the average squared distance. So normally to do the average, you add them up, divide by how many you have. Here I have average in quotes, so we're going to add them up, and then we're going to divide by 1 less than how many we have, okay? And there's a reason for doing that, but it's beyond the scope of the course. It's called Bessel's correction. You can go online and look it up, but all right, it has to do with the degrees of freedom, the fact that one of these is determined by the mean. Okay, so average squared distance, so we're going to add them up and divide by n minus 1. Okay, so we do 64 plus 16 plus 0 plus 16 plus 64.
160.
And we get 160. And then we're going to divide not by 5, but we're going to divide by 4. Okay, so we're going to divide by 5 minus 1. Okay, and so our variance is equal to 40. And so my standard deviation will be the square root of the variance, the square root of 40. So my standard deviation here is 6.3246. Is that okay? All right, and so in the interest of time, I'm going to just fly through the same process for family C, okay? So I'm going to just write distance. We're going to subtract the 9 from each of these.
Two.
Okay, so my variance is going to be 2.5, and my standard deviation is going to be the square root of 2.5. And I get something 1.5811. I'm not sure if I did that too quickly, but I will have these notes saved, and you can always go online and kind of just work through it. Yes, question?
What would the standard deviation tell us in relation to the...
So again, I mean, when we looked at the ages of the family, and we said family D has a bigger spread, more dispersion than family C, okay? I mean, in this example, it was very obvious, okay? But in we can give us a number and we say, oh, the standard deviation of family D is 6.32. The standard deviation of family C is 1.58, okay? And you could have, family E, and maybe they have a bunch of kids also, and we can do an actual calculation on this standard deviation, and maybe it'll say like 2.7 or something like that. And this gives us an idea of how spread out the ages are, okay? The ages of family E, if their standard deviation is 2.7, is more spread out than in family C, where it was like kid, boom, 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 boom. All these kids are very close to each other in age, but they're not as spread out as family D, where, there's like a 4-year gap between each child, okay? Yes.
Why do we divide by n minus 1?
The reason why we divide by n minus 1, okay, I will just say is you can look it up, called Bessel's correction. And the reason why is because we're trying to estimate the population standard deviation based on a sample, and because the way we're calculating the standard deviation is distance from the mean, but that mean itself came from the sample itself, so it's biased because it's not necessarily equal to the mean of the population. We have to correct that using the degrees of freedom n minus 1. But I don't think you cared to know all of that, so. Anyway, just know that we do n minus 1. I can't simplify it any more than that 20-second explanation there. So if you want a formula, this formula for the standard deviation is this. It's S is equal to the square root of the variance, which is the distance from each x minus the mean of x, and we square that difference, and we add them up, and we divide by n minus 1. This captures the essence of what the standard deviation is. If you don't care for formulas, then don't bother, okay? I'm not going to force you to use the formula. Again, the idea is, you know, find the mean, and then subtract the mean from each value. Each x value, and this will give you the distance from the mean. And then you square that difference, square the distance, add up, and divide by n minus 1. And then take the square root. Okay, and I know many of you guys are still writing, but in the interest of time, I'm going to move on, and again, I will have these notes saved and posted online so you can refer to them. And this is page 20, okay, page 20 in the notes. All right. The thing about the standard deviation is we can get something called a z-score. All right? With a z-score, this is the distance. A value point is from the mean. The distance a data point is from the mean, but it's expressed in standard deviations. And so, so here, you know, for example, let's say adult women in the U.S. have a mean height of 64 inches. So that's 5'4". So let's say that's the mean height, okay? And let's say the standard deviation is 3 inches. So this is the amount of spread in the heights of women in the U.S., okay? I'm just making this up. All right, so a woman who has a height, who is 67 inches tall, okay, is 3 inches above the mean. Okay. Her z-score is +1. Is that okay? She's 3 inches above the mean. Each standard deviation is 3 inches, so her z-score is +1. Okay, so let's see a woman who is 58 inches, okay, has what z-score? A z-score of -2, right? This 58 is 6 inches below the mean. Okay, each standard deviation is 3 inches. So 54, so this is -6, this is below the mean, okay? And so this will give us a z-score of -2. So we can think of a z-score as being our x value, and we're going to subtract off the mean to see how much above or how much below we are from the mean. And we're going to take that difference and we're going to divide by the standard deviation s. So this is our distance from the mean expressed in standard deviations. Okay? And here I did simple examples, but you can have decimals. Okay? So you can have, if a woman has a z-score of +1.5, how tall is she? If her z-score is +1.5, she would be 68.5, right? 68.5, right? So if z equals 1.5, her height would be is 68.5, right? Because she'd be 1.5 times the standard deviation above the mean. So she'd be 4.5 inches above the mean. Okay. So the thing about z-scores is we can now make comparisons between very different things. Okay. And we can say this is more extreme than the other thing. Okay. So we can say, what is more unusual, okay? Okay, we'll say a Chihuahua that weighs 8 pounds or a Great Dane. So these are both dogs that weighs, 200 pounds. Okay. Well, in order to answer this question, we need to know something about Chihuahuas. We need to know something about Great Danes. Okay. And so I did a little bit of research. You can go on Google yourself, and you can find out, a Chihuahua. As far as Chihuahuas go, these are these little tiny dogs. The average weight of a Chihuahua is something around 4.5 pounds, okay? So maybe 4.5 pounds, okay? And the standard deviation for Chihuahuas, just for simplicity, we're gonna say is 1 pound, okay? They're really tiny dogs, okay? For Great Danes, these are much bigger dogs. The average is something around 160 pounds. And the standard deviation is around, we'll say, 25 pounds. Okay? And so let's calculate the z-score for the Chihuahua that weighs 8 pounds. Okay, so 8-pound Chihuahua. The z-score for this dog would be 8 minus 4.5 over 1. Okay? So 8 minus 4.5, this gives me a 3.5 in the numerator and a 1 in the denominator. This dog has a z-score of 3.5. As far as the Great Dane goes, we're going to do, again, x minus the mean divided by the standard deviation. This Great Dane weighs 200 pounds, right? So we're going to do 200 minus the mean is 160 divided by the standard deviation S of 25. So I'm going to have 40 in the numerator, 25 in the denominator. 40 divided by 25
That's 8 over
is 1.6. Okay, so I have a z-score of 1.6. Okay, so Chihuahua, the z is equal to 3.5. Great Dane, the z is equal to 1.6. Okay, so we'd say 3.5 is farther from 0 than 1.6. So it is more unusual. All right, I might go maybe 5 minutes over, and I apologize, okay? I know, it's the worst. Okay. So here we have that. So this is, so you can start making comparisons between things from different groups, okay? If you have a little bit more information, such as the mean and standard deviation of the group from which it came, you can say, oh, this Chihuahua that weighs 8 pounds, that's really, really big for a Chihuahua, okay? Versus the Great Dane that weighs 200 pounds, that's a big dog, but in comparison to other Great Danes, it's not that much bigger, okay? And you'll read about the empirical rule in the textbook. And in general, what this means is z-scores greater than 2 or z-scores less than -2 are unusual, and z-scores greater than 3 or z-scores less than -3 are highly unusual. Okay. So those are just kind of the empirical rule gets into more detail there. All right. Okay. We have the other measure of dispersion. So the first measure of dispersion was the standard deviation and variance, and the other measure of dispersion is the IQR, the interquartile range. Okay, and so the IQR, the interquartile range, this is defined as the difference Q3 minus Q1. So what is Q3 and Q1? Q1 is known as the first quartile. Okay? Or we can think of this as the 25th percentile. This is the spot in the data where 25% or 1/4, 25% of the data is smaller. Q3, this is the third quartile, or the 75th percentile. Okay, it's the spot in the data where 75% of the data is smaller. So what does this look like? Okay. Well, let's say we have a set of numbers. Okay. So we'll say to find the quartiles, you first find the median. Okay. And then use the median to split the list into two smaller lists. Okay, and then find the, quote, median of those smaller lists to get the quartiles. All right, so let's say I just have some data here. So we have some people's ages. We got 20, 22, 24. So we're going to put these in order from least to greatest. Okay. So step 1, find the median. Okay, so I have a total of n equal, I've got 12 numbers, 12 values. So the median is going to be the spot where I split the list into 6 greater and 6 smaller, right? So the median will be 31 plus 37 divided by 2. I get a median of 34. Okay. So now I have the upper half, and then I also have the lower half. Okay, so we'll start with the lower half. I've got 6 values in the lower half. I'm going to find the, quote, median of these 6 values. So I'm going to split that right here. So I've got, just looking at the lower half, I've got 3 that are smaller and 3 that are bigger as far as the lower half goes. Can you guys see that? So this is going to be Q1. So Q1 is going to be 24 plus 26 divided by 2. Q1 is equal to 25. So using that logic, what is Q3? 43. It's halfway in between here and here. This is going to be Q3. 42 plus 44 divided by 2 gives me 43. Okay. So my IQR is Q3 minus Q1. I have 43 minus 25. One last, very last slide, and I promise that will be it. And I apologize. I'd really try to get you guys out of here on time, but I just want to cover one last thing. And it's like okay, so just the very last slide, and if you didn't catch all of that in writing, that's okay. Again, all of this will be posted online. So the final way to display things is with a box plot, okay? And a box plot looks like a box with a line somewhere here, and then 2 lines coming out of it, okay? And then maybe you have some dots, okay? The box is defined by 3 values. Q1, the median is this middle line, and you have Q3, okay? Sometimes they put like a little diamond to indicate the mean, but I would say that's non-traditional, okay? The little lines that come out of it, these are called whiskers. Okay, and then if there's dots out here, these are called outliers, okay? You can also have outliers on the low end too, okay? That's also possible. There is an invisible boundary that separates the outliers from everywhere else, and these are called the fences. So this is a fence and this is a fence, okay? But they don't appear in the actual plot. They're just there in the calculation of the box plot, okay? The key thing is that the width of the box is equal to the IQR, okay? The IQR is a way to measure dispersion, right? If something has a big IQR, those numbers are spread out. If something has a small IQR, those numbers are not spread out. Width of the box is the IQR. You can look at a box plot and look at the width and just say, lots of spread or little spread, okay? And then the other key thing is that the median okay? It's indicated right there. That middle line is the median, and that gives you an idea of the center, okay? So again, the median tells us the center. So we can look at, you know, kind of two box plots. We can see that middle line and compare the center. Is the center of one higher or lower than the other? We can look at the width of the box, and we can look, you know, identify immediately, is there lots of dispersion or little dispersion? Okay, I apologize sincerely for going over time. Have a good week. We'll see you guys